All right, so this is our presentation for our stress strain curve for the tensile test for both our aluminum and steel dog bone material specimen. These are two graphs for our aluminum Young's modulus and the steel Young's modulus for our specimen. And when we're looking at these stress strain curves, we first need to determine what exactly we're dealing with here. And these graphs look kind of confusing. There's no formula that fits into it, but these are all data points, right? So we need to first understand what exactly is elastic and Young's modulus, and what exactly that does for steel, what exactly that does for aluminum. So elastic modulus represents the stiffness of a material, and we calculate it by dividing the stress by the strain. And we find the stress and the strain by dividing the applied force by the cross-sectional area of the sample, which is going to be little sigma divided by the force over the area. And we find strain by dividing the length, or the difference in length, over the original length. So it's going to be basically the original, or the new versus the old. And in this graph, this is the linear graph of our aluminum and steel. And in these points, or in these parts of the graph, both of them obey Hooke's law, and it would go back to the original position afterwards.
This indicates the stress level at which each material permanently deforms after an external force is applied. We find the yield point by seeing the peak of the stress strain curve after which the stress drops. We identify the highest stress value, called the upper yield point, and the lowest stress value as the lower yield point. In this case, the highest yield point of the aluminum specimen is approximately 320 kilonewtons. The lowest yield point of the aluminum is 160 kilonewtons, while its maximum yield strength is approximately 280 kilonewtons. The gap between the maximum and minimum yield strength of steel and aluminum show that the steel is much tougher than aluminum, while aluminum is much more brittle than steel, but strong.
After looking at a yield point, we need to understand what tensile strength is. Tensile strength can be identified as the maximum stress a material can withstand before the fracture. One can see in the graph the highest point on the graph.
So in this scenario, it's like one of these points.
We can then calculate tensile strength. It's calculated by maximum force divided by original cross-sectional area. A real-world example is paperclip. Although both a paperclip and pipes, this specimen are made of steel. It is much easier to bend a paperclip as the cross-sectional area is very low. So its strength is much less than something like a pipe. Let's understand why this material deforms. Ductility must deal with a lot when trying to understand why an object deforms. Ductility is the ability of a material to deform under tensile stress before fracturing. We identify it by using percent elongation and percent reduction.
So in this scenario, the ductility of a material would be the length of the material initially, subtracted with the length of the material afterwards, divided by everything after. And you could also take this formula and multiply it by 100 to get the percent of ductility. And it's the exact same scenario for the resilience of a material, which is going to come up in the next part. And when we talk about resilience, we need to understand exactly what it means once again. Resilience is a material's ability to absorb energy during elastic deformation and then release it upon unloading. And when it does that, it rolls back to the original position. So back to the first graph, when we were talking about this earlier, from the point of initial pressure all the way to this point that I picked out, or not picked out more so, but this is the point when it stops being a linear graph. From this point to this point, all of the forces that are being put on this object or this material are going to be linear. And all of these forces are going to follow this path, which obeys Hooke's law, as mentioned earlier. And in this case, if you were to put any amount of force, if you put a couple 100 pounds of force from here all the way to like right at the edge of this, if you stop and go back to the original, your material will go right back to the original position. So if you're taking like a spring and you stretch it out real long and you stop stretching it, then you let go, it will bounce right back to the original position. However, in our test, we go past this and we get into this region called plasticity, which is where the graph starts to be more curved and not as linear. And when we do this, it's like taking a spring once again. If you take the spring and spread it really, or pull it really, really far, it's going to permanently deform and not be in the same position. Think of it like a pencil spring. If you take apart the lead pencil and spread and pull it really long, it's going to stop and not go back to the original position. Same with a paper clip, you pull it, it goes right back. And in the resilience of a material, the formula UR equals to little sigma y squared over 2E. Little sigma y squared is the yield strength. So this is going to be the stress at the elastic limit. E is going to be a Young modulus, which is what we mentioned earlier. This is also known as the elastic modulus, which is how far we can take it before it goes back down. And the formula is derived by the area under the linear portion of the stress-strain curve. So in this is a graph that we're going to go through afterwards. But from this point to this point, where it's a linear graph, that's where you would find the linear portion of the stress-strain curve. Taking the area of this is how you would find the resilience of a material.
Toughness is quantified as the area under the stress-strain curve up to the point of fracture. This represents the energy per unit volume that the material can absorb before breaking. Toughness is typically measured using impact tests such as the Charpy impact test and the IZOD impact test. These tests involve striking a notched specimen with a pendulum and measuring the energy absorbed during the fracture. The difference in the pendulum's height before and after impact gives a direct measure of the absorbed energy.
So in this case, we don't use any of those parts, but we do just do a tensile test. Can you go up? Xander, scroll up.
No.
We'll cut this. And in this case, we don't use neither the Charpy impact test nor the IZOD impact test, but we do use a tensile test. And this is just a very, very brief showing of how the toughness would relate. So in most people's minds, you would think, hey, aluminum is going to be less strong than steel. Steel is always used in different things. And we can even see that in this graph here. So back to here, the peak strength of aluminum was around 320 units. The steel, however, was only around 270 units. However, if you look over here, the steel lasted a lot longer under that force, although it didn't peak as high. And that's because steel is a lot tougher than aluminum. So aluminum will be a lot more brittle. So if you were to pull apart aluminum, it fractures right away. If you have a little paper clip, then you can bend it a whole lot before it starts reaching plasticity and breaking. But if you take aluminum foil, you can rip that very easily. And finally, in the Spider-Man clip that we were made to review, I pulled apart we pulled apart three frames of what's going on. And initially, you can see that there's a lot of tension in the spider silk. And spider silk is lots and lots of small strands all wrapped up together. And in this test, or not in the test, but in the clip, you can see initially it's very, very tense. However, as it starts breaking and fracturing, you see a lot more of the pieces of silk kind of exploding. And at the very end, you see the whole entire string just snap. Now, the reason why this is although spider silk is very, very strong or very, very tough, it is not very, very strong in general. So if you were to take a string, for example, you can hang on a rope for however much you want, but the second you try to lay it down and compress it, it's just going to fall right through. And finally, the webbing that he used was able to stretch and absorb a massive amount of force. And due to this, it could hold two parts of the ferry that were falling apart together, which is why the spider's strength was so strong. And that's it.